So my name is Nathan Marz. I work at Twitter, and today I am talking about Storm. So I just want to start off with some basic information about the project. I open sourced it on September 19th at Strangeloop. The implementation of Storm is about 15,000 lines of code. About half of that is Java, and half of that is Clojure. So it's a pretty small code base, but as you're about to see, it packs quite a punch. Storm has been adopted by over 25 companies since being open sourced, and it just has a very active community and very active ecosystem and very active mailing list. So before I get into Storm, I want to start off by talking about how we built these kind of real-time systems before we had Storm. And by doing this, we can dive into what are some of the intricacies of real-time computation that necessitated a new system. So the paradigm we used before Storm was the queues and workers paradigm. Very, very common technique for doing this kind of stream processing. We certainly were not the first ones to try this. So here's an example of what our architecture looked like using queues and workers. So we were reading the Twitter fire hose, and we were producing various analytics on those tweets. So we take the tweets and we put them onto a cluster of queues, and then we would have one set of workers that would take the tweets, put them into our schema, and then append those tweets to Hadoop for later processing. And then they would send messages to another set of workers that would update statistics on URLs that are being tweeted into Cassandra. So we did things like number of tweets per URL over time, impressions per URL over time, and things like that. Now, one of the interesting things happening here is that we actually necessitated that for any given URL, that it would only be processed by one worker. And the reason for that is because when we're doing updates in Cassandra, well, Cassandra doesn't have transactions, and at the time didn't have atomic counters, so you needed to make sure only one worker is updating a given key at once, or else you have a race condition, and they're going to trample each other, and you're going to lose data. Now, the way that we implemented this to make sure the same URL always goes to the same worker is when the first set of workers is passing the message to the second set of workers, they do mod hashing on the URL to choose the worker to go to. So basically, every worker has its own queue and only reads from that queue. Now, there's a lot of problems with this architecture, but you can see some of the problems emerge as you try to scale a system like this. So let's say that our bottleneck is the workers that are updating Cassandra, and you need more workers doing that processing. Well, in order to scale that part of the system, you need to go ahead and deploy that new worker and configure a new queue for that worker. But then, worst of all, you actually need to reconfigure and redeploy that first set of workers because they need to know that there's now new workers so that they can do their mod hashing appropriately. So you see these like cascading changes throughout the computation to get things to work. So scaling was one problem with this system, very painful. Another problem is that the fault tolerance of a system like this is very poor. You're kind of responsible for making sure your queues and workers stay running. There's things you can do with failover, but it all turns out to be very manual and very tedious. And then lastly, coding these things is very tedious. You spend most of your time worrying about where am I going to send messages to, where do I receive messages from, how do I deal with serialization. The actual real-time logic you care about ends up being a small percentage of your code base. So we looked at this architecture we had, as well as a variety of other real-time problems we were working on. And we came up with this list of things that we want from a good real-time computation system. So first of all, a real-time computation system must guarantee data processing. It's just important. It's important for most of our applications and just for most applications in general. Second, it must be horizontally scalable, but not just horizontally scalable, but easily horizontally scalable. So just add some nodes, tweak a few knobs, and have everything just work. Third, it must be fully fault tolerant. So if anything goes down or there's any errors during processing, the system should self-heal and keep on running. The fourth property is interesting, because here I say we want to get rid of all of those intermediate message brokers. Right? So if you look back at this diagram, between every set of workers, you have this cluster of queues. Now, the problem with those queues is that, well, first of all, they're complex because they're pervasive throughout the whole architecture, and it does persistence, and also slow. So rather than send messages directly from the producer to the consumer, you have to route through a third party who has to persist, which ends up being a pretty big mess. But the thing is that the reason those intermediate message brokers were there in the first place is because they help with guaranteeing data processing, that first property we want. The idea being that if a worker fails to process a message, it can just replay it where it got it from, and only take it off the queue when it finishes processing the message. So if we get rid of those intermediate message brokers, we need a whole new way of guaranteeing data processing. Fifth, we want a higher level abstraction than message passing. Message passing is clearly too low level for this kind of processing. And we want something that takes away of all that boilerplate. And then lastly, a real-time computation system needs to be extremely robust. So as a point of comparison, let me use Hadoop. So Hadoop is a batch computation system. It's a high-latency batch computation system where computations typically take a few hours or sometimes much longer than that. Now, Hadoop is, I don't know how many people here use Hadoop, but it's notorious for being difficult to operate and giving you just crazy stack traces. You need to dig into the implementation of Hadoop so you can figure out the obscure configuration that you need to tune so that you can get the whole thing working again. So it's very common to have to take a few hours of downtime on your cluster. But in some ways, that's okay for Hadoop because Hadoop is a high-latency system. So if you take a few hours of downtime, you're still high latency. With a real-time computation system, you take a few hours of downtime, you're no longer real-time. So the robustness requirements are much, much higher. And of course, Storm satisfies all these properties. I obviously would not have mentioned them if it didn't. So there's three broad use cases for Storm. These are by no means all-inclusive, but it's a good way to think about the kinds of problems it can be applied to. So the first I call stream processing. So the idea here is that you're processing a stream, like let's say a stream of tweets, and you're updating databases based on those tweets, and then you just drop the messages. The second is called distributed RPC, and I'll talk a lot more about this later on. The idea here is that you have some function that's really intense to compute, and you want to compute it on the fly. It's too intense to compute on one machine. So you can actually implement that function on top of Storm, and then use Storm as an RPC mechanism, where Storm can automatically parallelize your computation. And the third I call continuous computation. So the idea here is that you have some function where you want to know the result of it continuously. So let's say like computing trending topics off of the Twitter fire hose. So Storm cluster has three classes of nodes in it. On the left is Nimbus, which is the master node. It plays a role similar to the Hadoop job tracker. Nimbus is where you submit your topologies for execution, and Nimbus will take care of launching workers around the cluster to execute your topology, and it'll monitor your computation and restart anything as necessary to keep things running. In the middle is a Zookeeper cluster. Zookeeper is actually an Apache project. It's a really useful project. It's basically built for doing cluster coordination and configuration management. And this is exactly what Storm uses it for. So on the right, we have a set of worker nodes. So each worker node runs a process on it called the supervisor. And the supervisor communicates with Nimbus through Zookeeper to determine what should be running on that machine. And the supervisor will start and stop workers on that machine as necessary, as dictated by Nimbus. So let's say you have a computation you want to run on a cluster. So this is how you would launch it. There's a command line client that ships with Storm called Storm. And you would say Storm jar, give it a jar containing your code and dependencies, and then tell it the class to run and the arguments to that class. So we'll go ahead and upload your code to Nimbus, and then submit your topology for execution. And then Storm computations actually run forever, or until you kill it, like this, Storm kill, and then the name of the topology. All right, so let's dig into the abstractions of Storm. So there's four main abstractions: streams, spouts, bolts, and topologies. So streams are the core data model in Storm. When you're using Storm, you're manipulating streams and transforming streams. And a stream is just an unbounded sequence of tuples. And a tuple is just a named list of values. Your tuples can have whatever types you want in them. If it's a type that Storm doesn't already know about, it's very easy to just register your own serializers so Storm can handle it. Spouts are a source of streams in a computation. So an example of a spout would be a spout that reads from a kestrel queue and emits that queue as a stream of messages. Or maybe your spout connects directly to the Twitter streaming API and emits a stream of tweets as messages. Then there's bolts. So bolts process any number of input streams and produce any number of new output streams. So most of your logic with Storm goes into these bolts. So bolts do everything from run functions, do filtering, do streaming aggregations, streaming joins, talk to databases. Like I said, most of your logic goes into these bolts. And finally, the top-level abstraction in Storm is called a topology. So topology is just a network of spouts and bolts, where every edge in the graph indicates a bolt that's subscribing to the output stream of some other spout or bolt. Now, the key to Storm is that spouts and bolts are inherently parallel. They execute as many tasks across the cluster. So if you look at a topology as it's executing, it looks something like this. So every circle, every little circle there is like a task running somewhere on the cluster. And the tasks communicate directly with each other by passing messages around. So like the spout on the left has 2 tasks, the bolt on the top has 3 tasks, and the other 2 bolts have 2 tasks. So this is just a different view of kind of the same thing. So this is the logical view of your spouts and bolts, and this is the physical view of your nodes. So you can see here, like spout S has a task on the bottom left node and the top node. Bolt B1 has tasks all over the place, and then the tasks are just communicating directly with each other. Okay, so spouts and bolts are parallel. They execute as many tasks. Well, this brings up the question of when a task emits a tuple, to which task does it send that tuple to? Right, so here we have a diagram of a bolt with 3 tasks on the left, sending messages to a bolt with 2 tasks on the right. When a task on the left emits a message, to which of the 2 tasks does it choose to send the message to? So you answer this question in Storm by providing what's called a stream grouping. This just tells Storm how to partition the messages to the consumers. So the simplest kind of grouping is called a shuffle grouping. So in this case, it just picks a random task to send the message to. This has the effect of evenly distributing the load of the processing across all the consuming tasks. A more interesting kind of grouping is called a fields grouping. So here it chooses the target task by doing mod hashing on a subset of the fields of the tuple. So this should sound awfully familiar to what I was discussing in my first example with the queues and workers system, except this is now at a much higher level of abstraction. Another kind of grouping is called an all grouping. So in this case, it actually replicates the tuple to all the consuming tasks. Obviously, this can cause serious blow up at tuples, so it should be used with care. Then there's global grouping. So in this case, you pick the task with the lowest ID. This has the effect of all tuples going to the same task. And there's a few other kinds of groupings, but those are beyond the scope of this talk. So if you actually look at a topology, so if you look at what a topology looks like again, it actually looks like this, where every subscription edge is annotated with the kind of stream grouping used. All right, so let's dig into some code for using Storm with Clojure. So the example I'm going to show here is streaming word count. So the idea here is that we want a topology that takes in an input stream of sentences and produces an output stream of word counts. We just emit a new count for a word every time we see that word again. So here is how you would define the topology for this computation. So you use this topology function to create the topology, and then you give it a map of spouts and a map of bolts. And it's a map from a name for the spout or bolt, and then the value is just the implementation. So here we say we have a spout that we're going to call spout, and the implementation is in this sentence spout var, which I'll show the implementation of in a second. Then we have our 2 bolts. The idea is that the sentence spout emits a stream of sentences, and then we have a split bolt, which takes a stream of sentences and emits a stream of words. And then we have a count bolt, which takes in a stream of words and emits a stream of word counts. So here's how we define our word splitter bolt. So we say we're going to call it split, and we use bolt spec to create the bolt. And here we say, first we give it its inputs. What does it consume? So here it says, I consume the stream coming out of the spout component, and I'm going to use a shuffle grouping to consume that stream. And then the implementation is in that split sentence, which we'll look at in a second. And then we give this a parallelism of 5. So that means there will be 5 tasks executing this bolt across the cluster. And then here's the word counting bolt. So this consumes its input from the split bolt that we just defined. And this is doing a fields grouping on the word field. So this has the effect that the same word always goes to the same task. And this is actually very important for this computation. So like imagine we used a shuffle grouping for that portion. Well, then the same word may go to different tasks, and each of those tasks may have a different view of how many times that word has appeared in the past, and it wouldn't be able to emit the right count for that word. By doing a fields grouping, then we know the task that sees that word has seen every instance of that word, and then it can emit the right count. And then this bolt is given a parallelism of 6. So here's the implementation of the sentence spout. So use this def spout macro to define it. So here it says, we're going to call it sentence spout. It emits a stream with one field called sentence. And then what this does is that every time this next tuple function is called, it emits a random sentence from these sentences listed there. Okay, so let's define our first bolt. So here's the split sentence bolt. So this takes in a stream of sentences and emits a stream of words. So this bolt emits a stream with one field called word. And then every time it receives a new tuple, you can see it just splits the first value of the tuple, which is the sentence, on white space. That gets the words. And for each one of those words, it emits the word as a one tuple. There's a few other things going on here, which I'm going to explain in a few minutes. Okay, and then finally we have the word counting bolt. So this bolt is a little bit different than our last bolt because it needs to store some state about what's the count for each word. So you can see it uses this prepare true option, and that lets you create a closure over your actual function that does the processing. So here in that closure, we just store the word counts in just an in-memory hash map. I'm doing it this way just for simplicity. You could use a database or something. Then you can see every time it gets a tuple, it updates its in-memory map and then emits the new word count. So it's really quite simple. Okay, so now let's say you have this topology and you want to run it on a cluster. So the code for doing that looks like this. You say storm submitter, submit topology. You give your topology a name. Then you give your topology a configuration. So the configuration is used to tweak various aspects of how it runs. So here we say we want this topology to run across 3 workers. The idea here is that there'll be 3 physical JVMs spawned for this topology, and all your tasks for your spout and bolts will be evenly spread across those workers. And then you pass it the actual topology that we just defined. You can also run topologies locally, just completely in memory. And this works by actually just simulating a whole storm cluster in process. So here to run a topology in local mode, you create a local cluster object, and then you submit your topology to the local cluster in the exact same way as you submit to an actual cluster. So here it looks the same, except for a configuration, we set topology debug to true. This has the effect of logging a message every time a message is emitted, or logging to console every time a message is emitted, which is really useful for debugging, as you can imagine. Okay, so let me do a quick demo of this. Okay, so here's the code, the exact same code I just showed you. So I'm just going to run it. Cool, so now it's running. So it's running in local mode, and I set it up to run for 10 seconds, and then it'll automatically shut down. Okay, so it finished. So now if we just look to see what happened, so here you can see like the sentence an apple a day keeps the doctor away was emitted by the spout. And then you can see the word splitter bolt picked up that sentence and started emitting some of the words. And kind of in parallel with that, you can see that the word count bolt is also running, and everything is interleaved because everything is running in parallel. So yeah, that's it for word count. Okay, so the next thing I want to talk about is distributed RPC. This is one of the really cool use cases for Storm. So like I was saying in the beginning, the idea behind distributed RPC is you have some really intense function that you want to compute on the fly, but it's too intense for a single machine, so you want to distribute the computation to make it fast. So here's how the data flow works for distributed RPC, which I'll just refer to as DRPC, on top of Storm. So the idea here is that you're on the left, you're a user who has some function you want to execute, and you have some arguments for that function. So what you do is you talk to this server called the DRPC server, and Storm comes with an implementation of this. You tell the DRPC server, I'm going to execute this function, and here are the arguments to my function. What the DRPC server does is it coordinates the actual computation, and it makes the DRPC look like regular RPC. So you make the function call, and then your request blocks, and then the DRPC server acts as a spout for a topology that actually implements that function. Now, the stream that spout emits is a stream of function invocations. And each tuple in that stream contains a request ID for the function, the arguments for that request, which is what was provided by the user, and then the return info for this function invocation. So the return info is just the host and port of the DRPC server. So your spout picks up that function invocation, and then it can go and take that tuple and do its thing and compute the function. And then at the very end of the topology, you send the result to a special bolt, and then that bolt then connects to the DRPC server and sends it back for this request ID. Here is the result that was computed. And then the DRPC server maps that request ID to the waiting client, unblocks the waiting client, and sends them the result. Right? So from the client's perspective, it looks just like normal RPC, but it's actually executing in parallel in the background. So let me give an example of DRPC. So the example I'm going to use is computing the reach of a URL on the fly. Now, what the reach of a URL is the number of unique people exposed to a URL on Twitter. To compute reach, you have to take the URL, you have to get all the people who ever tweeted that URL. Then for each of those people, you have to get all of their followers. So now you have a potentially massive set of followers. And you have to take that huge set and distinct it, and then you have to count the distinct set, and you get the reach. So this is a really intense computation that, for something like, let's say, a TechCrunch URL, can involve hundreds or thousands of database calls and tens of millions of tuples to process, all that they have to do in real time. Our initial implementation of reach before we had Storm just ran on a single machine, and for some URLs would just take like more than a minute to run. It was really brutal. With Storm, we got it down to 2 seconds for the hardest URLs. So this is really cool stuff. So the topology for reach looks like this. It's very straightforward. So you have your spout that's emitting function invocations. So it emits a stream containing a request ID and a URL. So your first bolt is called getTweeters. So it takes a stream containing a request ID and a URL and emits a stream containing a request ID and a tweeter ID, right? So one URL tuple maps to many tweeter tuples. Then you have a getFollowers bolt. So this maps a stream containing request ID, tweeter ID to a stream containing request ID, follower ID. You can see getFollowers does a shuffle grouping on tweeters, so it evens the load of fetching the followers from your social graph store. So the next bolt is called partial distinct. So what this does is it does a fields grouping on the getFollowers output stream, and there's a fields grouping by the follower ID. So this has the effect of the same follower goes to the same task of partial distinct. And each partial distinct task kind of aggregates the whole set of followers for this request ID, and when it receives the whole set for that task, emits the count of that set. The reason this works is because it does the fields grouping by follower ID, each task in partial distinct receives a mutually independent subset of all the followers. Right? So they can each emit kind of part of the count for the reach, and then all that's left to finish the reach computation is to sum up all those partial counts. I hope that makes sense to everyone. So as you can see in this topology, the entire computation from getting the followers, doing the uniquing, and doing the counting is completely parallelized. So here's what it looks like in Clojure. This actually, this linear DRPC Clojure abstraction isn't released yet, but it's going to be out soon. But I just want to show you guys what it's going to look like. So here's how you create this topology that I just showed. So you just say linear DRPC topology. And what this thing does is it kind of automates all the boilerplate of DRPC, so like setting up your spout, setting up the bolt at the end to send the results to the DRPC server. So you just plug in the steps of your computation, and that wraps it with everything else in the topology. So what you say is you say, okay, my first bolt is get tweeters, and we want a parallelism of 3. My next bolt is get followers, and it does a shuffle grouping, and it has a parallelism of 12. My next bolt is partial distinct. It does a fields grouping by follower ID and has a parallelism of 8. And then count aggregator does a global grouping, right? So it's pretty much identical to the diagram I showed. Actually, it takes up less space, which is cool. So get tweeters and get followers are very straightforward. They take a tuple, and they just do something with just that one tuple. So partial distinct is a little bit more interesting because it actually has to process like batch of tuples. It needs to know what are all the followers that were sent to me for this request ID. So the way partial uniquer works is that you use this thing called a batch bolt. So def batch bolt partial uniquer, and this lets you actually process batches of tuples as a first class thing. The way it works is so you get a new one of these instances for every request ID. So you can see it's parameterized with the request ID on that second line. And then it keeps in a closure the set of followers that is seen for this request ID. Then every time it receives a new tuple, it updates that follower set with the follower that it was given. And then when it's received all tuples for the batch, this finished batch function is called, and then it just emits the request ID and then the count of the set for to emit the partial count. That's it, and then a count aggregator is another similar pattern, and that's it for reach. Okay, so I talked in the beginning about how Storm gets rid of all those intermediate message brokers and chooses instead to send messages directly from producers of messages to consumers of messages, which is really important for lowering complexity and making things faster. But like I said, Storm, by getting rid of those intermediate message brokers, Storm needs to do something different to guarantee message processing. So let me go into how that works now. So first you have to decide, what does it even mean to guarantee message processing? Well, the first thing to look at is what happens to a message, like a source message in a topology, like a message that comes off a spout. We'll look at a message that comes off a spout, and so here I'm using the word count example. So we have a sentence that's emitted, and that sentence goes to some bolt, some word splitter bolt. And that word splitter bolt now emits a bunch of messages based on that first message, right? So we emit a word for every word in that sentence. So you can see like each of those word tuples has a dependency on that original sentence tuple, right? And then those tuples, those word tuples, go to the word counting bolt, which then emits the updated count, and there's kind of a dependency with that original word tuple. And then those tuples may go to more bolts, which may generate more messages, and so on and so on. So you end up with this tree of messages, which were all spawned by that original spout tuple. So Storm calls this tree of messages the tuple tree. And the way Storm defines whether you've successfully processed a tuple coming off the spout is a tuple coming off the spout is fully processed when the whole tuple tree has been exhausted and every individual node in that tree has been acknowledged as complete, that you're done with it and you're finished with it. Now, if you are unable to complete a tuple tree within a specified timeout, then the spout tuple is replayed, which will just cause the entire computation to regenerate. That timeout defaults to 30 seconds, but it's, of course, configurable per topology. So there's a little bit of work you need to do to take advantage of this reliability API, but it's pretty simple. The first thing you need to do is tell Storm whenever you're creating a new edge in that tuple tree. So this is you do this by doing this is called anchoring. So here's that split sentence bolt I showed before. So when we emit a new word tuple, we anchor it to that input sentence tuple. So that creates a new edge in the tree. And then you tell Storm whenever you're done with a single node in the tuple tree You do that by calling this ACK function, which is marks it as complete. And Storm does the rest of tracking the tuple tree and determining when it's complete, and then sending an appropriate message to the Spout to tell it you're now done with that tuple and can get rid of it. So you might wonder, like, okay, how does it track these tuple trees? Isn't that going to be really memory intensive? What if you have tuple trees with like 1 million pending tuples, right? Is Storm going to have to track actually 1 million tuples? Are we going to have memory problems? Well, it turns out that you don't need to explicitly track the tuple tree to do this algorithm. So like, regardless of how big the tuple tree is and how many pending messages there are, Storm only uses a constant amount of space to track the tuple tree. It's about 20 bytes, regardless of the size of the tuple tree. It's a really cool algorithm for doing this. It's documented on the wiki. It's one of the keys to Storm for why we're able to do this efficiently, so that we can get rid of those intermediate message brokers and reduce complexity and make things faster. Okay, so now I want to talk about transactional topologies. So this is a relatively new feature in Storm. So one thing you may have thought of during the presentation of guaranteed message processing is, all right, so when something fails, you replay from the spout, but that means sometimes you can have the same tuple processed multiple times, right? So Storm provides in its core functions an at least once delivery guarantee. So you may wonder, okay, so how do you do something like counting with an at least once delivery guarantee, right? Like, aren't you going to overcount? So Storm solves this problem with a feature called transactional topologies. The cool thing about transactional topologies is that it's built completely on top of Storm's primitives of streams, spouts, bolts, and topologies. And what it enables is fully fault-tolerant, exactly once message processing semantics. Okay, so the model of transactional topologies is a little bit different. So the idea is, instead of processing one tuple at a time, we're going to process small batches of tuples at a time. And if any part of a batch fails, you replay the whole batch. You reprocess the whole batch. Now, the processing of a batch has two phases. So you process it, and then you have a commit phase for the batch. And any number of your bolts can participate in this commit phase. Now, what transactional topologies provide that you don't have in normal topologies is a strong ordering on the commits. So the idea is that, like, if a commit fails, you'll replay the commit, but you don't move on to the next commit until that commit succeeds. So if you actually look at how the commits happen in practice, like, you might try to commit batch 1, and that may fail, so you'll redo batch 1 and you'll commit it again. Let's say that succeeds, then you move on to batch 2 and you commit batch 2. That succeeds, you move on to batch 3, you commit that. That succeeds, you move on to batch 4, you commit that. Let's say that fails, you'll redo that commit, and so on, right? So the commits are strongly ordered, possibly with repeats, to retry the commits to deal with failures. Now, this strong ordering that's provided by Storm is sufficient for you to get exactly once messaging semantics. So let me show you how that works. So here is a bolt that updates like a count in a database, idempotently and fault tolerant, so that you get that exactly once messaging semantics. So you can see this bolt, we say this is a committer, so it participates in the commit phase. I'll explain what that means in a second. So this is the batch bolt like I described before. So it's parameterized with the ID for this batch, and that's that attempt variable you see there. And that contains like the transaction ID or an ID for this batch. So the way this bolt works is that in the execute method, we aggregate the partial count for this batch. And then in the finished batch method, we're going to update the database by adding our partial count into the count in the database to update the count. So the way it works is that, so let me go back. So let's look at how finished batch works. So it gets whatever the current value is in the database. Now, one thing we're going to do different than you may do normally when you're doing something like this is that rather than store just the count in the database, we store the count as well as the transaction ID. So let's see why we do that. So So here's the key line in this whole thing, which is we only update the database if the transaction ID stored in the database is different than the transaction ID of this batch. Okay? So the idea is, let's say I go to commit. Let's say I go to commit and I have, let's say 5 tasks participating in this commit, each updating some different part of the database. Now let's say 2 of those tasks succeed and 3 of them fail. Right? So we have to retry the whole commit. Well, the ones that succeeded will go back to the database and see, oh, the transaction ID in there is the same as what I'm currently processing. So I won't update the database because I know that the database already reflects the batch that I'm responsible for. So it skips the update. Whereas the other tasks, the transaction ID is different, so it'll just go ahead and update the database. And the reason this works is because of the strong ordering in commits that Storm provides. Cool. And just a shout out, I got the idea for this trick from the Kafka developers. It's a really cool trick. And I think Storm takes this idea of storing the transaction ID in the database and doing a strong ordering to its extreme conclusion. So one of the cool things about transactional topologies is that you can actually pipeline the computation. So you can actually process multiple batches in parallel, but the commits of the batches will be ordered. So I could be like committing batch 1, but you can still process batches 2 through 10 in the meantime, but just don't commit them, right? So while batch 1 is updating the database, batches 2 through 10 can be computing their partial counts, or whatever is the intermediate computation for your application. So one thing about transactional topologies is that they require a more sophisticated input source or input queue than something like Kestrel or RabbitMQ. But Storm Contrib has a transactional Spout implementation for Apache Kafka that I mentioned, which means the stuff basically works out of the box. So just a few more tidbits on Storm. So Storm comes with a UI, which is similar to the Hadoop UI. So the UI tells you what topologies are running on the cluster and then provides you with detailed statistics about the processing. So it tells you things like what's the throughput through every component, what are the latencies on each bolt, and then it tells you things like what's the complete latency on each spout. So that's the total amount of time it took for the tuple tree to be completed. This is really, really useful. One other note, Storm has a companion project called Storm Deploy, which is a one-click deploy tool for EC2. This is written using Palette, which is a phenomenal library. And this just lets you get up and running very, very quickly. Finally, the Storm Starter project has a bunch of example topologies for just getting up and running very quickly. Finally, also Storm has a lot of documentation, so check out the wiki. I think there's over 20,000 words of documentation now. I've gotten good feedback on it. I think it really helps people get started. All right. Thank you very much. Can I take any questions? Like, how does it know when it's received, like, the whole batch? Yeah, so the DRPC stuff is like a higher level abstraction on the primitives of spouts, bolts, streams, and bolts. So the way it works is that, so one of the stream groupings I didn't mention before is called a direct grouping. So in this case, so normally when you do a grouping, it's the consumer that decides, I want to read the stream from here, and here's how I want you to partition it. Now, direct grouping works a little bit differently, where the producer, it's more traditional, where the producer can actually pick the task to send the message to. So the way it works underneath the hood is that every time you like emit a message, like all those like emit functions I showed, they actually return the sequence of task IDs that message went to. And then what you do is that when you're processing a batch, it keeps track of how many tuples it sent to every task, and then it sends a direct message to each of those tasks with a number of messages they should expect to receive. And that provides sufficient information for them to detect when they receive the whole batch, and then to call that finish batch method. I hope that makes sense. Yeah, it's a good question. So the deal with fault tolerance with Nimbus or the supervisors is the Nimbus and supervisor daemons are designed to be stateless and fail fast. So like if Nimbus, let's say the process crashes, that doesn't actually affect the computation. The topologies keep running, which is, if you use Hadoop, is in contrast with Hadoop, where if you kill the job tracker, all your jobs die. So if Nimbus goes down, nothing happens to the actual computation. What you lose when Nimbus is down is now it's no longer being monitored So if you lose another node, well, nothing's going to go and restart those workers. So it is important to keep the Nimbus node up, but it's okay if the process crashes or the machine reboots or whatever, because nothing catastrophic will happen. It won't just like kill your topology. Eventually, we want to add like clustering to Nimbus so that you have like failover and stuff. But in practice, because the process itself is resilient to failure, it tends not to be that important in practice. So topologies can be cyclic if you want. I've never actually had that use case, although there's a few users that do that. So you're asking, what does it mean that it's scalable, right? So you saw that like in the topology definition, you specify the parallelism at each step, and then you deploy it, right? So when you deploy a topology, it's static, right? Like it's going to run with that many workers and that many tasks, and it'll spread it across the cluster. If you want to like scale a topology, what you do is right now you have to just take it down and then redeploy it with new parallelism or new number of workers, which isn't like perfect. Eventually, we want to implement a feature called swapping, where you can tell Storm, I want to swap this existing topology with this new topology. The way that will work is that it'll actually deploy the new topology and like allocate all the resources for it and like get it running, but it'll launch in an inactive mode so that it's not actually doing any processing. And the idea here is that once it's up, it can then do a switch between the two topologies. So I'm going to deactivate this one and then activate the new one so that you only take like a second of downtime rather than a few minutes for doing the redeploy. Correct. Yeah, that's an interesting question. So how do you deal with spiky traffic? So right now, we just buffer on the source queues to Storm. So eventually we want to implement auto-scaling. So technically, Storm has all the information it needs to know how much parallelism should be at each component, right? So it should be able to just dynamically scale for you. We're not there yet, but that's definitely in the long-term goals. Correct. Yeah, but then that would deal with spiky data very, very well. Okay, so I think I'm out of time, but I'll be around, and thank you guys very much.